Welcome to the second part of Lesson 1. In this section, we are going to be focusing our efforts on learning how to draw and interpret organic structures. Specifically, we will learn how to accurately and efficiently draw complex molecules using what are known as skeletal structures. We will also start to learn more about the chemical bond, orbital hybridization, and the concept of functional groups. To get us started drawing structures, we need to take a moment to review a few common patterns we see in the geometry of molecules. The guiding principle when we are trying to predict the three-dimensional geometry of a small molecule is that the terminal atoms, the atoms bonded to the central atom, and any non-bonding electrons, will be as widely separated in space as possible due to electron-electron repulsion. For example, you probably remember from your previous course in chemistry that when a central atom is connected to only two other atoms, or groups of atoms, the molecule adopts a linear geometry around the central atom. The bond angle here is 180 degrees. We can see the repulsive effect of non-bonding electron pairs when we look at the bent geometry shown here. The central atoms, in the cases shown here, each have either one or two non-bonding electron pairs. In both cases, this causes a change to the geometry. Because of the repulsive forces of the non-bonding electrons, a linear geometry cannot be adopted. Notice that when there is only one non-bonding electron pair on the central atom, as in nitrite, the bond angle is less compressed than in the water molecule, which has two non-bonding electron pairs on the central oxygen atom. This increased crowding causes smaller bond angles. When we have three atoms bonded to a central atom, and that atom does not have any non-bonding electrons present, the terminal atoms are able to separate by 120 degrees in a single plane. This is called the trigonal planar geometry. If we add a non-bonding electron pair, or a bonding atom, we get to the next two possible geometries, which are called trigonal pyramid and tetrahedral. Both geometries have four groups around the central atom, and the bond angles are both 109 degrees. To summarize, there are three principal geometries we have discussed. First, when a central atom has two groups around it, we get a linear geometry. The bond angles are 180 degrees. Second, when a central atom has three groups around it, we get a trigonal planar geometry. The bond angles are 120 degrees. If one of the groups in a trigonal planar geometry is a non-bonding electron pair, the shape of the molecule is described as bent, and the angles are still 120 degrees. Third, when a central atom has four groups around it, we get a tetrahedral geometry. The bond angles are 109 degrees. In a tetrahedral geometry, if one of the groups is an electron pair, the shape is described as trigonal pyramid. Bond angles are 109 degrees. If two of the groups are electron pairs, the shape is described as bent. But notice that this version of the bent shape has bond angles of 109 degrees. There are many different ways to draw structural formulas for organic compounds, as we have developed different methods that work well in different situations. Some of these drawing styles were developed for printing structures in textbooks, whereas others are used to help analyze the spatial relationships between atoms. Here are a few examples of different drawing styles. One drawing style, which is called an extended structure, depicts an organic molecule as a flat, two-dimensional drawing that explicitly shows all of the carbon and hydrogen atoms, along with the bonds between them. These structures can be helpful when one is first learning how the connectivity of carbon and hydrogen work, but they are also quite cumbersome and tedious to draw. They also tend to obscure what is important about a structure with unnecessary clutter, in the form of the letters C and H. Another style is called a condensed structural formula. In condensed structures, the bonds between carbon and hydrogen are omitted. This has the benefit of being easy to type and print. One drawback of this method is that it requires the reader to unpack and expand the formula into a complete structure. This can cause confusion and unnecessary errors, and we try to avoid using them except in the simplest possible examples. A more modern approach is to use something called a skeletal structure. Sometimes these are also known as zigzag structures. In skeletal structures, carbon and hydrogen atoms are not written explicitly with the letters C and H. Instead, the skeletal structure depicts carbon atoms at places where the zigzagging lines intersect, and also at the endpoints of lines. Also, all of the hydrogen atoms that are necessary to give carbon 4 bonds are implied, so we don't need to draw them. These skeletal structures have many benefits. They are quick to draw, and they show the most important structural features for a molecule, without obscuring them with unnecessary detail. In this class, we are going to use skeletal structures most of the time. On the next several pages, we are going to be practicing some of the guidelines for drawing skeletal structures shown below, so please familiarize yourself with them. Finally, this last drawing style looks completely different than any of the others. This is called a Newman projection, and they are very useful when we are thinking about three-dimensional positions of atoms around a molecule. We will come back to Newman projections a bit later. To get started understanding skeletal structures, let's look at a few examples and see how we can translate a skeletal structure into an extended structure that shows all of the carbon, hydrogen, and heteroatoms. Let's start with the first example, 1-butanol. When we are looking at a skeletal structure, we need to translate the lines into a series of carbon atoms bonded to one another. In skeletal structures, carbon atoms are located at the endpoints of lines, and the intersections of lines. So we can see that in this molecule, we have 4 carbon atoms, one at each of the locations I have designated with a dot. The 4th carbon atom in the chain is bonded to the oxygen atom, which in turn is bonded to a hydrogen atom. Notice that in the skeletal structure, all heteroatoms, such as oxygen, nitrogen, sulfur, and halogens, are always explicitly drawn. Also notice that any hydrogen atoms connected to heteroatoms are also drawn, whereas they are omitted when bonded to carbon. Another point to note is that it is very common for us to see structures that omit non-bonding electron pairs, even when they are present. Similar to how hydrogen atoms are left off of skeletal structures, we can also omit explicitly drawing non-bonding electron pairs, as it is assumed the correct number must be present, based on the formal charge of the atom. So if you see an atom without any electron dots drawn, it definitely does not mean the electrons are not there. They may or may not be. It is your job to know. In this case, let's actually draw these electron pairs on our extended structure. Let's do the same translation for the next example. Notice that I am starting by drawing the carbon backbone first. Once I have completed this part of the structure, I can start connecting the various heteroatoms, some with single bonds and others with double bonds. Now I can go ahead and add in the hydrogen atoms. Since this carbon already has 3 bonds, it only needs 1 additional hydrogen atom to make it complete. Finally, I get to the terminal carbon atom, which needs 3 hydrogen atoms to be complete. Let's work on the final example, limonene. Limonene, you will notice, contains a ring of carbon atoms. We can draw the extended structure like this, with 6 carbon atoms connected in a cyclic formation. Now, let's attach the other carbon atoms that are attached outside of the ring. Once we have all the carbon atoms in place, let's make sure to draw in any multiple bonds, as those will change the number of hydrogen atoms that are possible. There are 2 double bonds in the structure. Now, let's fill in all the hydrogen atoms. Pause the video for a moment and see if you can fill in the correct number. When you unpause the video, we will review the solution. Okay, so now that you have drawn in the hydrogen atoms, compare your answer with the following. Notice that when a carbon atom already has 4 bonds to other carbon atoms, we don't want to place any more hydrogen atoms. Were you correct? Nice work! Let's go to the next page and start drawing our own skeletal structures. Now that we can interpret skeletal drawings, let's try drawing a few. I will start by converting the structure shown here, called isoprene, into a chain of carbon atoms using zigzag lines. The horizontal chain has 4 carbon atoms, which looks like this as a skeletal structure. Notice that it does not matter which direction my zigzag lines are going, as they are still 4 carbon atoms connected together in the same way. Just like real molecules rotate and spin around in space, so too can our structures of them. To complete our structure, I need to attach the branched CH2 group, which is connected to the main chain with a double bond. I also need to add a double bond to the first atom. There. This is the skeletal structure for isoprene. But what if I had drawn the structure like this instead? Or like this? Are these still isoprene, or are they something different? If we look at each one carefully, we can see the connectivity is identical. It is just that they have either been rotated or flipped. Soon, we are going to be learning a systematic way to name molecules, and it turns out this will also help us better understand situations like this, and avoid getting confused. For the next example, please pause the video and see if you can make the conversion into a skeletal structure yourself. When you unpause the video, we will look at the solution. Okay, so now that you have drawn the skeletal structure, you should have something that looks like this. You may have a slightly different structure, so let's discuss a few possibilities. A common mistake that students make at this stage is drawing skeletal structures with bonds pointing in the wrong direction, like this. While this is technically still a correct answer, the problem lies with the way that this bond is oriented. When you are drawing skeletal structures, notice that the carbon backbone alternates between carbon atoms that are pointing up and those that are pointing down. When a carbon atom is pointing up, any additional bonds on that carbon will also be pointing up, not down. Similarly, when a carbon atom is pointing down, any additional bonds also point down, like this. If we refer back to the structures drawn over here, illustrating this common mistake, we can locate the error. Notice on the first example that the OH group was drawn on a bond that is pointing up, but the carbon it is attached to is pointing down. Compare that with the correctly drawn structure above, and you can see the difference. On a down-pointing carbon, branched bonds should also point down, and vice versa. Now that we have had a little practice drawing with skeletal structures, and interpreting what they mean in terms of the connectivity of carbon atoms, let's go to the next page and learn about the concept of isomers. As you are learning how to draw organic structures, you are probably also starting to think about the different ways that one could construct a molecule, simply by arranging atoms differently. This concept, which you may have encountered in previous chemistry courses, is called isomerism. Isomers are compounds that have the same composition, that is, they are made out of the same type and amount of matter as each other, but they are different in some other way. That is the key distinction. Isomers are fundamentally different compounds, even though they are made out of the same stuff. We are going to see there are several different types of isomers that can occur. Sometimes the difference is based on spatial arrangements of atoms. Other times, as is shown in the example below, it is based on a difference in connectivity between the atoms. As discussed earlier, a covalent bond results when two atoms can share electrons with one another, so that they can achieve a more stable state. How exactly do the atoms share electrons with one another? The atoms share electrons by the overlap of orbitals. Overlap of atomic orbitals can occur in several different ways, depending on the orientation and shape of the orbitals that are interacting with one another. In this class, we will be learning about two ways that orbitals can overlap to form bonds. These two modes of bonding are called sigma bonding and pi bonding. For now, let's focus on sigma bonding. Sigma bonding is a type of covalent chemical bond that forms when two atomic orbitals overlap directly between the nuclei of two atoms. It's the strongest type of covalent bond. In a sigma bond, the electron density is concentrated along the internuclear axis, which means it's directly between the two bonded atoms. Sigma bonds can form between atoms of the same element or different elements, as long as their orbitals can overlap effectively. Sigma bonding frequently occurs by something called end-to-end overlap of the atomic orbitals. End-to-end overlap occurs when the lobes of the orbitals all lie on the same axis as each other, as is shown in the diagram below. The concept of orbital hybridization was introduced to provide a more accurate description of molecular geometry than what could be achieved using pure atomic orbitals. In simple terms, hybridization involves the combination of atomic orbitals, such as s, p, and d orbitals, to form a set of new, hybrid orbitals that are more suitable for bonding. As an example, let's consider the molecule methane, which has the formula CH4. In methane, the central carbon is bonded to the 4 hydrogen atoms with 4 sigma bonds. These bonds all have the same length as each other, and they are arranged in a tetrahedral geometry. To achieve this configuration, we cannot use ordinary atomic orbitals as they are around an isolated carbon atom, because there are 2 different types of orbitals, with different sizes and shapes, and they are not oriented in a tetrahedral geometry. Instead, we will take the 4 atomic orbitals, an s orbital and 3 p orbitals, and convert them into 4 new hybrid orbitals. These new hybrid orbitals are a mathematical blend of the orbitals that were mixed together, and they are called sp3, to indicate how many of each type of orbital was used to construct each one. The resulting sp3 orbitals have a tetrahedral arrangement in space, with bond angles of approximately 109.5 degrees between them. Each sp3 orbital contains a single lobe that is larger than the other, because of the sum between the s orbital and one of the p lobes, and they are oriented in such a way that they are directed towards the corners of a tetrahedron. We can see how the entire process works in more detail by looking at the orbital filling diagram for carbon, both before and after the hybridization. Notice that we are hybridizing the orbitals in the valence shell, as these are the orbitals that will be used for bonding. Also notice that when the 2s orbital is hybridized with the 3p orbitals, the new hybrid orbitals are evenly populated with the valence electrons, and each of the hybrid orbitals needs a single electron in order to close the shell. The hydrogen atoms in methane will form 4 sigma bonds to carbon, through an overlap between the hydrogen 1s electron and the sp3 orbital it is interacting with. A graphic of this is shown in a few slides. This mode of bonding, called sp3, results in a tetrahedral geometry around the central atom. We will see this is the most common way that carbon forms 4 bonds, but we will also see there are other ways the orbitals can hybridize as well. These other hybridization modes will allow us to form double and triple bonds. They will incorporate not just sigma bonding, as is shown here in the sp3 mode, but they will also have pi bonding. More on that later. As mentioned previously, here is a graphic showing the sigma bonding that occurs between the hydrogen 1s orbitals and the carbon sp3 orbitals in methane, along with the tetrahedral geometry. Not all covalent bonds have an equal distribution of electron density between the 2 bonding atoms. Bond polarization refers to the uneven distribution of electrons within a covalent bond, leading to the formation of a partial positive charge on one atom and a partial negative charge on the other atom. This phenomenon occurs when atoms with different electronegativities share electrons in a covalent bond. At one extreme of bond polarization, the atoms become completely ionized, due to a very large difference in electronegativities between atoms. This results in the transfer, rather than sharing of electrons, otherwise known as an ionic bond. At the other extreme, we can have two identical atoms bonded together. Because these atoms are of the same type, they have the same electronegativity, and therefore the electrons are shared equally between the two atoms. In the middle of these two extremes, we have polar covalent bonds. In a polar covalent bond, the electron pair forming the bond is not shared equally between the atoms involved, due to differences in their electronegativities. As a result of this uneven sharing, the atom with the higher electronegativity gains a partial negative charge, denoted as delta minus, because it attracts the shared electrons more strongly, leading to an accumulation of electron density around it. The atom with the lower electronegativity is left with a partial positive charge, denoted as delta plus, because it loses some electron density to the more electronegative atom. This charge separation creates a dipole moment across the bond, where one end of the bond is slightly positive, and the other end is slightly negative. It's important to note that in a polar covalent bond, electrons are still shared between the atoms. However, they are shared unequally, due to the differences in electronegativity. This contrasts with an ionic bond, where electrons are completely transferred from one atom to another. In organic chemistry, a functional group is a specific group of atoms within a molecule that determines the molecule's chemical properties and reactivity. Functional groups are responsible for the characteristic reactions and behaviors of organic compounds. These groups typically consist of atoms such as carbon, hydrogen, oxygen, nitrogen, sulfur, and sometimes other elements. Functional groups can be classified into several categories, based on their chemical properties and bonding patterns. On the next several slides, I am going to introduce you to some of the most common functional groups. You will need to commit these functional group patterns and their names to memory. You should be able to write the name, the general formula, and at least one example for all of the functional groups presented on these slides, before the first quiz. Here are the common functional groups we will start with. Hydrocarbons. A hydrocarbon is an organic compound composed solely of hydrogen and carbon atoms. These atoms are bonded together in various arrangements. The four types of hydrocarbon functional groups you need to know are as follows. Alkane. An alkane is a hydrocarbon that contains only single bonds between the carbon atoms within the molecule. As such, they are known as saturated hydrocarbons. Alkene. An alkene is a type of unsaturated hydrocarbon that contains at least one C-C double bond. Alkyne. An alkyne is another type of unsaturated hydrocarbon, but in an alkyne, the unsaturation occurs through the presence of at least one C-C triple bond. Aromatic compounds, also known as an arene. Aromatic compounds are cyclic unsaturated hydrocarbons that contain a series of single and double bonds that can be interchanged in resonance forms. Moving on from hydrocarbons, we introduce our first heteroatom, oxygen. When we have a single bond from carbon to oxygen, the two main functional groups to consider are called alcohols and ethers. In alcohols, we have a saturated sp3 carbon atom bonded to an OH group. The OH group is known as the hydroxy group, and it is the characteristic feature of an alcohol. The other functional group is called an ether. In an ether, we have a COC bonding pattern, which is known as an alkoxy group. Our next set of functional groups are those that contain a structural feature known as a carbonyl group. A carbonyl group is a substructure that has a carbon doubly bonded to an oxygen. For example, the functional groups aldehydes and ketones both contain a carbonyl group within their structures. Notice that with an aldehyde, the carbonyl carbon has a bond to a carbon on one side and a hydrogen on the other. This distinguishes it from a ketone, which has a carbon on both sides. Two other carbonyl-containing functional groups are carboxylic acids and esters. In carboxylic acids, the carbonyl group is bonded to a carbon on one side and a hydroxy group on the other. Contrast this with the ester functional group, which also has a carbon on one side, but an alkoxy group on the other. Our next set of functional groups are those that contain nitrogen atoms. When we discussed common bonding patterns for nitrogen, in part 1 of this lesson, we observed how nitrogen can have 3 single bonds, as in 2 of the functional groups shown here. Notice that both amines and amides both contain a nitrogen that has 3 single bonds and a non-bonding electron pair. The only difference between amines and amides is that in amides, the nitrogen atom is bonded to a carbonyl group. So, amines are a functional group that has nitrogen with 3 single bonds, whereas amides have a carbonyl group bonded to an amino group. Amino is just a term to describe a substructure where nitrogen has 3 single bonds. What are these other 2 functional groups? One is called an imine. That is the functional group where nitrogen has a double bond to a carbon and single bond to a hydrogen, or another carbon atom. The other is called a nitrile. A nitrile has a nitrogen with a triple bond to a carbon atom. Moving on, we have 2 sulfur-containing functional groups. Sulfur is analogous to oxygen, and you can see that these functional groups are the sulfur analogues of alcohols and ethers. When a saturated sp3 carbon is bonded to an SH group, the functional group is called a thiol. When a sulfur has 2 single bonds to 2 saturated carbon atoms, it is called a thioether. Our last 2 functional groups are those that contain halogen atoms. When a halogen atom is bonded to a saturated sp3 carbon, the functional group is called an alkyl halide. Alkyl is a term that means saturated hydrocarbon. So, an alkyl halide is a saturated hydrocarbon that contains at least one halogen atom. We can also bond a halogen atom to a carbonyl group, as is shown in the second example. This functional group is called an acyl halide. They are also frequently called acid halides, because they are derived from carboxylic acids. That concludes our introductory list of functional groups that you must know. That also concludes the second part of Lesson 1. Let's move on to the third and final part of the lesson.